Finding local extrema again! Yay! I know, you really didn't get enough the first time, so I thought we'd do it again. No, just kidding. Now that we have talked about the first derivative and the second derivative test, we can now talk about finding local extrema a different way. And this is called the second derivative test for local extrema. So we're going to suppose that f double prime is continuous on an open interval containing C, where f prime of C equals 0. So this point C is our possible critical point. So if the second derivative of C, so if we take the second derivative and we plug our critical point in, if f double prime of C is greater than 0, or positive, then C is a local minimum. And yes, that is correct. I didn't mess up. When the second derivative is positive, we have a local minimum. Then when the second derivative of C is negative or less than 0, we have a local maximum. So when we're talking about second derivative test, you got to think opposites. And then finally, when the second derivative of C is equal to 0, that tells us absolutely nothing about our local extrema, so therefore you'd have to use some other form to figure that out, such as our table or such as the graph. Alright, so let's look at an example. Use the second derivative test to locate the local extrema. And look, we have our friend 3x to the fourth minus 4x cubed minus 6x squared plus 12x plus 1. And we've already done all of the work for this guy, so we now just have to put the pieces together and analyze the results. Alright, so we found out the first derivative of this guy was 12x cubed minus 12x squared minus 12x plus 12. And then we set this guy equal to 0 because we're looking for our critical points, which are our possible local extrema. And when we did this, we were able to determine that x is equal to positive or negative 1. And again, these are our critical points. Now that we have our first derivative and we have our critical points, in order to use the second derivative test, we do need to find, that second derivative, which we have already found the second derivative before, which is 36x squared minus 24x, and I wrote 12 for some reason, so let's fix that, minus 24x, and then minus 12. Alright, so now we need to take these two critical points and we need to plug them in our second derivative. So we'll plug in negative 1 and 1. And when we do that, we are going to get 36 plus 24 minus 12, which is going to be equal to 48. And then we are going to get 36 minus 24 minus 12, which is going to be 0. Alright, so now let's look at our critical point x equals negative 1. 48 is greater than 0, which means we have a local minimum. And that x equals 1, our second derivative equals 0, which means our second derivative test is inconclusive here. Which means we would have to use some sort of table like we've done before, or look at the graph. But our second derivative test tells us nothing about that. So, then, based on our results from the second derivative test, second derivative and test, we know that x equals negative 1 is a local minimum. And again, at x equals 1, the second derivative test is inconclusive, so we don't know anything from that. And that is it, ladies and gentlemen. If you have any questions, please let me know. Please come see me during my office hours, message me on Canvas, email me through email, or catapult your message to me, and I will see you next time.